right, good afternoon. Welcome. So first, before we begin, just to let you know, the expo hall is open. So we're standing between you and the party at the expo hall. So we'll try to make this fit within the time frame. But welcome to Practitioner's Guide to Data for Generative AI. I'm Jonathan Katz. This is Siva Raghupathy, who has been at AWS since
2009.
2009. So he's seen a lot with data throughout the years. And he's going to come in at the end of the presentation and tie everything we're talking about all together. So Siva, thank you for briefly joining me on stage.
Thank you, Jonathan.
Yeah, you're welcome. And the context to give this talk is it's all about data flows. You've probably heard a lot about vector databases, vector search, and generative AI. But the magic of generative AI is really taking all of those private data sources you've built up over the years and bringing them into these foundation models to give these very rich personal responses. So this is a level 300 talk, which means we're going to try to get into as much of the technical details as possible, but this is a very wide-ranging topic, and the goal is we're going to give you as many strategies as possible to make informed decisions as you're building out these generative AI applications. And what better way to do that than through an example? So let's dive right in and talk about Pat. Pat needs car insurance. This is probably something that you're all familiar with in some way. I mean, who's bought car insurance before? Right? And it's probably something that we can build a virtual AI assistant to be able to help with. But just going to buy car insurance can be kind of complex because there's driving history, accident records, payment history, how much you've paid before, which car insurance providers you've used before. And to do that, we need to be able to pull from a lot of different data sources to deliver that personalized experience, plus also understand nuance in language. Because Pat comes in and says something like, I'm interested in getting car insurance. And that phrasing is very important because interested can mean a lot of different things. Is Pat researching car insurance? Is Pat ready to buy car insurance? And that can ultimately dictate the workflow. So as we come and we're trying to deliver that response, we need to understand how do we take all of that data that we have and deliver that rich experience or that personalized experience. And the technique that has been established to do this is called retrieval augmented generation. Who's heard of RAG? Cool. Well, you're in for a treat because this is pretty much going to be the entirety of the talk is discussing RAG. Because to understand how we bring in our different databases to RAG, we need to understand how RAG works. And we're going to be going into very detailed workflows in terms of the different RAG techniques that have emerged and how data gets involved in it. So let's take this question. I'm interested in getting car insurance. If you go to a foundation model that's just trained on publicly available information, you're not going to be able to deliver a response of any value. But if you bring in the private data sources, things like driving history, payment history, accident record, you can probably be able to deliver a detailed quote. So as the first part of this talk, we're going to walk through what this first call and response will look like, and then we're going to start building in more workflows that incorporate more data sources and techniques to enrich this application. And the key thing to know is that to get from the user question to the augmented prompt, we need to understand where our data is coming from. And there's two types of context to think about. First, there's situational context. Tell me about this person that's here, or what's the current situation, what's in the current session. So for things like this with Pat, it's going to be location, driving history, car specifications. These are facts that we know about, about the current person that's asking. And there's semantic context. Semantic context is going to give meaning to the facts. So things like car regulations, photos, uploaded claims. Now, situational context probably exists in your databases already. In your traditional enterprise data stores. It could be relational databases, other operational databases, et cetera. Where semantic context is often dealing with transformed data. It's data that's in a different format that we need to put into a place that we can search over it. And this is where you probably have encountered vector databases or vector search engines. So what we're going to see in this example is where does all this data fit in? And if we're building an augmented prompt, what we need to look at the prompt is, well, these 4 steps. First, instructions for the foundation model. Things like, hey, we're building out like car insurance quotes, don't make things up. I don't want to be giving everyone free car insurance. Then the situational context. Here's the person that's logged in. Here's all the information about them. Make sure we're giving them, adding that specific information to that person. Then semantic context, the meaning behind it. Make sure we understand if they're in the state of Nevada, what are the regulations for Nevada in terms of selling car insurance? They might not match up with those in New York. And then maybe the user input. It depends on the foundation model. You might need to add that in or not. So the first thing is that we get the prompt instructions. So in this case, we want to have a friendly insurance agent that is delivering this information. Now, what does the prompt instructions have to do with the database? Maybe nothing. It could be hard-coded into your application. Maybe everything. You might have a prompt database that you need to pull from. But again, it's important to understand that flow as you're designing those applications. Then you have the situational context. And I can almost guarantee you this is coming from your database. But these are basically filling in the facts. And again, you might have a prompt that has the ability to interpolate that information, similar to like string substitution, where you put that information in. Then all the semantic information. If you need to be able to perform the search over, say, a document collection that has all the different rules and regulations and pricing, that will add that in. Finally, with the prompt. So what happens here? How do we actually build out this specific solution? So you have your users, they come in, they ask the question, and it goes to your application. So the first thing that's going to happen is that based upon the question, you're going to want to be able to access your prompt repository, which again could be hard-coded into the application. Maybe it's in a Git repo, maybe it's in a database. You pull that all in, and then you're going to retrieve the situational context, which is probably similar to what you've been doing with transactional applications to date. It's as simple as querying a database. Meanwhile, you're also going to take that user input and get a vector embedding. So the vector embedding is going to effectively transform what's in that user input and put it into a format where you're able to compare it against other semantically related things to be able to find the most appropriate response. So think of the vector as just a transformation. You have some text or images or video or what have you. You transform it into this mathematical construct so you can compare it against other text and images and video and effectively have a common language for being able to do so. And finally, you tie that all together, you send it to the generative AI model or the foundation model, and you get a response. And it looks something like this in a way, where if I'm pulling the situational context, in this case, it was a SQL query. Hopefully we're all familiar with that. And the semantic context, because we create an open search database, it's going to be an API call. Again, nothing new. We've been doing this for a long time. We're just pulling it all together, putting it into a prompt, and getting an answer. So based upon the prompt we had, we're going to have an answer like this because we said something like, hey, validate like all of Pat's information is real first before we proceed. So it spits out that information in natural language, and it's like, yeah, do you want to proceed? And Pat comes in and says, yes, that's correct, and gets a response back. OK, you're interested in car insurance. Well, car insurance in your area costs between $20,000 and $5,000. Do you want more information? The answer from Pat's probably going to be probably, because that's a very wide range. It's correct. It's semantically correct. That's the meaning that it has. But it's still not a great response. And that's going to be the name of the game of bringing in your data sources for generative AI. It's going to be about how do we enrich the semantic content to give the most tailored response, because it's going to have a cost if we keep having to go back and forth. So what have we done so far? So first, we've defined what situational and semantic context is. This is going to be very important as you build out a wide-ranging data architecture, because one, it's going to impact how you query that data and bring it in, but also it's going to be because you have to think about things like performance and timing, and ultimately, how do I minimize my interactions with my users? Because there's a cost here. It's not just the cost of querying the foundation model. Like certainly, there's a cost to be generating input and output tokens, and it could be quite substantial if you're generating a lot of them. But it's just like traditional application development. The old adage that the more clicks the user has to make, the less likely they're going to complete a transaction. Well, the more questions or the more answers a user has to give in a virtual AI experience, the less likely they're going to complete the transaction. So that you have to keep in mind that cost as well. So the focus of the rest of the talk is how do we optimize these interactions? How do we deliver as much semantic meaning to this data as possible? We're going to exploit the different RAG techniques and basically build a RAG foundation and look through how do we iterate and add more complex techniques as we need it. Then we're going to see how this fits into our overall data foundation, which effectively is not just understanding our data sources, but how do we prepare our data in a way so we can use it in RAG. And finally, we're going to see how to connect it all together, particularly if you have a data sprawl and all these different private data sources that can ultimately deliver a rich generative AI application. So let's have some fun. What's happened with RAG so far? How's it evolved? Well, first let's look at the workflow in RAG to fully understand what's happening. Let's say if we're trying to build our semantic data, we might have some PDF documents. we need to transform those PDF documents into sizable chunks that we can use with our embedding model, because an embedding model might not be able to read in a full embedding document. The embedding model takes that, transforms it into a vector, and then you can store it into some kind of vector database. So that's part one of adding semantic context to your application. That's the ingestion pipeline. The next part, which is the part that your customer will see, is the agentic workflow, where the customer comes in and asks a question. I'm interested in car insurance. I guess ask a question, make a statement. It's an implied question. It goes to the generative AI application, which then is also going to take that question, turn it into an embedding, perform a similarity search within the vector database, return the answer, and allow you to fulfill, augmenting the prompt and giving the answer to the user. So that's the agentic workflow. And these two work in concert because you need to keep your data fresh and up to date, for being able to search over your semantic context. And you also need to be able to, query it. That's ultimately the end goal of that. So several methods that we can use with RAG. The first is naive RAG. And this is a little bit of a misnomer because it is naive in terms of what we're going to see the workflow is, but it's really the foundational method. It's effectively that workflow we just saw where a question comes in, we perform a query against a database, we give a response, we call it a day. That might be good in a lot of cases, but as you just saw with Pat's insurance example, we didn't necessarily get the best response for that particular application. And this is where advanced RAG comes in, where there's different search techniques we can use to be able to access the data and provide more context. For example, maybe we have information about Pat's driving history that can help us narrow down what that actual quote is. And finally, there's modular RAG. We'll find with advanced RAG, you're often pulling from multiple data sources, and you have multiple knowledge bases set up, and you need a way to be able to choose between the different knowledge bases to be able to deliver the most accurate response at that time. Additionally, you might have a multi-step workflow where you have to query multiple resources at a given time to be able to generate that response. And the way you're able to further automate that can ultimately save you a lot of time. So what is naive RAG? Really, we should call it foundational RAG, but this is the fundamental workflow. This is where you're going to make the initial design and technology decisions, such as how you're going to prepare your data, as well as what are the different retrieval techniques. But really, it's about technology selection. What building frameworks are you going to use? Which foundation models and embedding models are you going to use? And also, what data stores do you need to bring in? What databases are going to use? What additional technology are you going to add to the stack? But really, this is about setting, as I keep saying, it's about setting the foundation. Even though it is a naive and simple workflow, ultimately it's iterative. As you add in advanced RAG techniques, you're able to bring in additional data, additional context to that. So let's look at a brief example. And again, this is, we're not going to build out a full code example, but we'll look at the open source framework LangChain, which provides a lot of the primitives to be able to implement a RAG workflow. And again, it should look like programming any other kind of application. You're just building this out for generative AI. I want to call out this situational context in particular. If you notice, we have a LangChain call in there, but also something that looks like, for those of you familiar with Postgres, calling the Python Postgres library. And that's fine. I think that's part of establishing situational context, which is you may be pulling from data sources that that you've been using all this time, and making those in this case SQL queries to be able to pull in the situational information. And there's the bar that's highlighting that. But one of the interesting things is going to be pulling in the semantic context, because remember, part of the building the semantic context and making it available to your users is that ingestion workflow, and that's going to be the magic word pipeline. Now, when I was an app developer, I think back to building out my first pipeline. I had an email management application, and being the naive app developer at the time, I was trying to do it all transactionally. Like something came in, send the email out, boom, done. As part of the web request. But then we'd be sending 100 emails at a time and 1,000 emails at a time, and those web requests were really slow. And I was like, well, gee, this doesn't make sense. So I built a pipeline. Basically, when it was time to send the email, I made a request, it put something in a queue, and it got processed asynchronously. And I thought that was really cool. But then I realized, oh wait, I have to manage like this asynchronous, email pipeline that had to build out all this monitoring and things. And again, this was a long time ago. It's a lot easier to do this now. But the point is that pipeline management can be challenging. So let's look at this example where we have a bunch of documents that are being uploaded. So what do we have to do? We take the documents, we split them to chunks, turn them into vectors. Then we have to store them. We have to store them in this case, our OpenSearch database. And then ultimately, we're able to perform similarity searches on it. But those first two steps are likely occurring asynchronously. So I need to make sure I have that code in a place where I can have it under constant management. This is where a feature like Amazon Bedrock Knowledge Bases comes in, because Knowledge Bases automates that part and basically handles the pipeline ingestion for you. So instead of having to write out the code to be able to manage your own pipeline, you can take Bedrock Knowledge Bases and say, all right, I have all these documents in an Amazon S3 bucket. Sometimes they get added, sometimes they get removed. But Knowledge Bases is going to detect that and update your vector database to be able to automatically add or remove rows or keep all the data fresh. And really, all you have to do is you have to sub out the library that you're using to be able to manage that. And the code actually becomes much more condensed, that instead of having to write all the pipeline management code, you have effectively the management console to be able to say, here's my chunk size, here's my destination for my data, here's the source of my data, stored in this database. I don't want to worry about that. I just want to focus on the similarity search aspects of it. So one thing to look at as you're establishing your data foundation is where can you automate things? Like where can you automate pipeline management? Your pipeline is not necessarily your differentiator. Your application is your differentiator. So being able to focus on having your data sources prepped and pulled into the application will help save you overall management time. So what are the trade-offs of naive RAG? Because even though I keep saying it's foundational RAG, I keep using this term naive. Well, it's very simple, and simple is good. Simple helps you get started, and it may work for a lot of different workflows that you have, but it might not necessarily capture the nuance of your semantic data. So again, back to the car insurance example, if I'm saying like, hey, car insurance for you is going to cost between $20,000 and $5,000, that's not a well-tailored response. Also, you might not be able to fully get all the guardrails you need into place, and we'll explore that in a second. But the point is that if we want to be able to get more personalized responses, we might need to combine multiple search methods to do that. And that's where advanced RAG comes in. So let's go back to this example. You may recall I said, Pat had 3 cars. And it turns out like one of the cars was in an accident, but Pat didn't own the car at that time. But however, if we just use this naive RAG technique, we might not be able to understand that because the agent looks at it and says like, oh, your second car was in an accident. I'm sorry I can't give you like our ultra super premium discounted rate. And Pat's probably gonna come back and say, wait, no, what are you talking about? I sold that car years ago. But the agent might not have enough information to fulfill that request because we just used a basic similarity search. So we need to be able to pull in more information to give that tailored response because at this point, Pat's like frustrated with the agent. It's like, I'm not buying car insurance from you. You don't understand my driving record. So let's look at a few techniques in advanced RAG that are going to help us bring in more context. So first, to understand the workflow of advanced RAG is that you have pre-retrieval tasks. So a question comes in, and you can do additional work to tailor the question. For example, you might add in guardrails, such as like, hey, don't complete the transaction in the agentic workflow. You're going to have to redirect to something else, or an agent, a human agent might need to take over. But there's other techniques to also pre-process the data, which we're going to explore. Then there's the context retrieval, where we're going to see multiple techniques for doing more advanced searches. And finally, there's post-retrieval tasks, which again, you might have some additional guardrails to filter down the data, or you might need to re-rank or summarize it, which again, we're going to see over the next few slides. So first technique, hybrid search. So hybrid search is one way to unlock more semantic meaning based upon the context of the question. So the example I talked about earlier was the word interested. What does interested mean? Is interested saying like, I'm just exploring if I want to buy car insurance? Or is interested like, oh no, I'm ready to buy, like, let's go. And we're able to use hybrid search to understand more around the textual meaning using full text search techniques, combine it with vector search, and ultimately provide a re-ranking over it. And this is a way where we're able to bring in both the meaning of the semantic relationships we've established with the embedding model and just the general text corpus that we've established. So we see hybrid search used in a variety of different ways. It could be around the content generation, summarization, sentiment analysis. But in some ways, it gives you another check on your data to make sure that you're really getting the best quality. So let's take this example. I'm interested in getting car insurance. This is one place we can add in a guardrail, which is making sure, hey, I want to make sure that the content that Pat is suggesting is not illegal, offensive, et cetera. But we can also get an additional ask, possibly like, hey, can you look into this meaning of the word interested? In this particular context, does it mean purchase? So because of that, if we rewrite it and say purchase, now let's do a different search. Let's do this vector search to see, across all the documents we have, what this word truly means. And let's do a text-based search, which we've been doing for a very long time, and we're going to see all the documents and what they mean. Pull them all together and get a result, and the idea is that we're boosting the relevancy of the result. If you think about vector search in terms of recall, which is the measurement of the expected results returned, this is a technique that can help boost recall. Now, like all good things, there's a trade-off. The trade-off is that your search speed might be a little bit slower here because now you're performing 2 searches, each with different latency times, and ultimately you have to re-rank them, and re-ranking is typically fast. But the trade-off is that if you get a better quality result, you can deliver a more personal experience to Pat who's buying car insurance. That's going to be a lot of the tension we're looking at these techniques, is that you're going to have to pay costs somewhere. But ideally, the cost, you want to be able to pay enough costs such that the return on that, the user experience or the end goal of the user, is going to outweigh the cost of maybe a slightly slower database response time. So next, GraphRag. GraphRag is another RAG technique that's able to, or is another search technique that's able to enhance the information in the RAG workflow because you're able to find more relationships between the data. So let's take this I'm interested in getting car insurance example again. In this case, we're less concerned about the meaning of the words in GraphRag. What we're trying to understand is Pat's car ownership history. Because remember, typically if you've been in an accident in a car, your car insurance premiums go up. And we know that it was a fact that Pat's second car was in a car accident. But Pat didn't own it at the time. And if we're able to have a graph of the data or a mapping of the data, we can see the lineage and say, like, oh, Pat didn't own this car. This other person owned this car, and they crashed at this time. And that's good because then we could say, like, oh, Pat is a low-risk driver. We can quote our most super ultra duper premium for Pat. So trade-offs, like advanced, with GraphRag, you're able to get more meaning behind the data, particularly if you created a lineage behind it. There's going to be a cost to it. There might be more time to be able to generate the query. You can use something like Amazon Neptune Analytics or Amazon Neptune to be able, which is purpose-built for searching graphs, and be able to perform that search there, and ultimately enhance the response. But ultimately, you want to use the technique that's going to make the most sense for searching that kind of data. Now, there's other things we can bring into advanced RAG as well, including context summarization. So one of the challenges with naive RAG is that, well, or just RAG in general, is that there's a cost to input tokens. If you have a lot of input tokens, you're effectively paying per token, and not everything within those tokens might have meaning. For example, if you're looking at the Nevada state insurance regulations for car insurance, which I personally have not read, but I'm sure they're very detailed, there's a lot of information. And there's a challenge with foundation models called the lost in the middle problem when there's too much information and may not effectively be able to summarize it into an appropriate response. However, there's a technique to deal with this, and that's called summarization, where you take, say, like the insurance regulations, and before you go to the big foundation model, you go to a smaller large language model. And the smaller large language model will likely return a fast response, but what it can do is it can summarize the insurance, like let's say the insurance regulations, down into like exactly what those are, like the key points. You take those in, you put them into the large foundation model, and then you take those, you have the summarized response, you put it into your prompt, and then you put that prompt into the large foundation model. Again, that's an effective technique to save cost and also give a better response, particularly when the source information is too much to be able to get anything meaningful when you're delivering ultimately the final response to your customer. What are some other advanced RAG techniques? One of my favorite, natural language queries. Now, I say that because I love writing SQL so much. That's probably, it makes me a little bit sad that natural language queries are getting so powerful, but at least I know SQL is not going away. But the point is that, despite that, not all questions that come to through a generative AI application really require transformation into a vector. For example, if Pat wants to understand, what was their car insurance last year, well, that sounds like, select star from, payment history where user equals Pat, where year, right? That kind of SQL query. In that case, what you could do is when the question comes in, if you have all that information, say in an Amazon Redshift cluster, you can get that schema, take that schema, go into an augmented prompt to understand, okay, here's all the relationships between the data, and ultimately output a SQL query. And the SQL query is your natural language query, which then you can choose to execute against the database and return a response. And what's very powerful about that is, again, if you don't have to transform your data, that's great. If you literally, you just have to take the question, transform it into a query, execute it against your data that's in place, and then get the answer, that's very effective. Because let's say you have all this data in a data warehouse that you're going to ultimately transform into vectors. There's a couple things that can happen. One, you can end up inflating your data because the vector representation may be larger than the source data, but then you're having to manage another pipeline. And remember back to earlier in the presentation, every time we have to manage a pipeline, that's more work that could ultimately be undifferentiated for the application you're building. So if you can query data in place, certainly do that. And you can even incorporate that in a generative AI fashion. All right, so we've covered quite a bit about naive RAG and advanced RAG. So when do you use each? Well, guess what? You're always using naive RAG because that's the foundational RAG. That was kind of a trick question. But when do you keep using naive RAG? Basically, if there's no logic involved, which, wait a second, we're working with computers. What do you mean? If you have something that's like a very simple Q&A, what color is the sky? I mean, that's probably a bad example. But with a private data source, like what, I should have prepared a better example for that. But basically, if you don't need, unlike me, if you don't need to think about the question, it's basically a fact in a database with semantic information, you can return that. But as soon as you start wanting more personalization, particularly around, I have all this meaning around, semantic meaning around car insurance rates that I want to be able to deliver to Pat for that response, you'll probably need advanced RAG. And again, this is good. Personalization in these cases are good, but understand the cost and where the cost trade-offs are. Do you want to pay more on the database portion of your query, or do you want to pay more at the foundation model? And ultimately, advanced RAG is, particularly as your applications mature, you likely will be deviating towards advanced RAG, or deviating is the wrong term. You're going to be iterating towards it, but it's going to help deliver a much better response. Now, here's the fun part. You've built up all these knowledge bases that has all this different information in it. How do you know when to use a particular knowledge base? Well, you can encode that into your application, but that's going to be hard because suddenly, you sort of need an agent for your agents in a way because you have all these different disparate data sources and you don't know when to use it. And it's kind of like when you're just thinking right now, I was thinking of an example, all right, which example do I choose? It's kind of similar to that concept. And this is where modular RAG comes in, because we want to make sure that we're choosing the right data sources at the right time. So this technique, this is an evolving technique, but this is quickly becoming very popular, is pre-retrieval query routing. This helps you choose between the different knowledge bases and different search techniques based upon the question that comes in. And here's an example using llama index code of querying multiple storage systems to be able to do this. And you can see that this gets quite complicated very quickly. And again, it almost feels like you're building out an AI model at this point to be able to decide what to do. And this is where a feature like Amazon Bedrock Agents comes in, because Bedrock Agents are going to help with the orchestration, these multi-step workflows where you might have to go to multiple sources to be able to curate the answer, or you might have to call out to multiple different services to be able to get the information to add in the answer. And again, anytime we can automate orchestration, we remove the undifferentiated heavy lifting. This has become my favorite term over the course of this presentation, because the more that we can automate, the easier it'll be to add in all the application-specific logic that you need. So here's an example with Pat's car insurance dilemma. So the question comes in, I'm interested in car insurance. First part of the workflow might be pulling in different context. And let's say a lot of the context is in the database, but maybe we have to query the DMV records directly because we haven't updated them. Or maybe we need to get Pat's claim history or credit report. So we can use the agent. The agent will know to automatically query that data based upon the context you give it. And then we might need to take some additional steps once we understand the context. So let's say Pat is going to be pre-approved for the car insurance, where we can go through all the different tasks, such as being able to get the insurance quote, updating the database to say hey, here's the insurance quote that we gave Pat on this different date, and so on and so forth. And this is pretty cool because ultimately, by going through this multi-step agentic workflow, on your side, after you set up the agentic workflow, this is just an API call. You make an API call to kick off this workflow. Agents does the hard work of going through all these different steps and ultimately delivering the answer to give Pat that car insurance claim. Finally, I'd be remiss not to talk about semantic caching because I keep mentioning how much or how little you may want to be able to query a foundation model. So semantic caching is a technique where if you have similar questions or similar prompts going to a foundation model, you're able to short circuit and not call the foundation model. And the cache can occur on multiple levels. It could be the question, the augmented context, or it could be everything, question, context, and answer. Now, the challenge with semantic caching is like everything with caching, which is the scope. If you have like a simple public Q&A chatbot, you can probably cache everything. But if it's tenant-oriented or user-oriented, semantic caching may or may not make sense based upon how much the particular model is being used. So for something like car insurance, that's probably going to be highly user-oriented, and it's probably going to be an individual interaction that using the caching technique may not necessarily make sense. But if you have a general chatbot that just talks about car insurance and the rules across the United States, that could be something where you could leverage semantic caching. So how does it work? Well, this is that typical agentic workflow that we see, but when the question comes in, or the question, the answer, context, whichever method you choose, you first check to see if it's in something such as Amazon Memory DB, where you can perform a vector search against that, see if it's there. If it's not, you go to the you go to the foundation model, you get the answer, and then you bring it back in and you store it in the Amazon Memory DB instance. With semantic caching, if you have a cache hit, you bypass that whole bottom half of the workflow. So one, you're going to get the answer back faster, which is great because who doesn't love speed? But also, you don't have to make the call to the foundation model, and so there's cost savings there. All right, so what have we done so far? So we've looked at how we prepare our data. We haven't looked at how we prepare our data yet. We've looked at the different RAG workflows and how we start bringing our data into them. But there's going to be an important step in terms of preparing our data, particularly for this one. Well, not for this one. We might need to prepare this one. So structured data. Structured data has a defined schema. There's meanings, there's patterns to it. Depending on what you're doing, you might not need to prepare it because you can make natural language queries against it. But we know the structure of it. This is likely going to be where situational context lives. Then there's semi-structured data, which is kind of weird because in my mind, this is still kind of structured data, but it's a less defined structure. So something like JSON, where JSON does have structure, but it could evolve over time. Or data residing in your data lake, where the schema for that data evolves over time. And this data, it could end up being your situational context. It could end up being your semantic context. So you might have to do some preparation. And then there's unstructured data, which we don't know what the meaning is. And this is where embedding models come in, because those embedding models are going to help give the meaning to the data. In this case, we will definitely need to make some sort of transformation of it. So let's start with unstructured data. How do we prepare it for RAG applications? Well, we talked about this briefly before, which is we have the source information, in this case a document, and we need to first chunk it up. Now, what chunking is that it's a way to take your document and put it into bite-sized chunks that you put into an embedding model. And in that embedding model, the embedding model is going to turn into vectors. The reason why we have to chunk it up is, in some ways, the embedding model might not be able to handle the full document, but it might also be cost. Even if the context window is large enough, it might not necessarily make sense to do that, and you might not actually capture the appropriate meaning of it. So we need to understand what the different chunking strategies are and what makes the most sense. So how do you pick one? Well, the quick start is something called fixed chunking, where you say, hey, chunk only so many tokens at a given time, like chunk 256 tokens. 256 because that's a cool number. And what's nice is that it's very easy to build, but it might not fully capture all the context that you need for the particular problem that you're trying to solve. So for example, notice, I tried to color code all this here. Hopefully the color code makes sense. But let's say we're looking at the Nevada regulations insurance document. If we're just taking it in chunks, we might miss the meaning on a particular regulation. And particularly it's a regulation, meaning law, that could be bad if we miss that context. So then there's schematic chunking, or if you have a defined schema, we can use structural chunking. And again, this is nice because it's kind of like a pseudo structured document or semi-structured document, particularly if we're parsing something like HTML. And again, like if you have a defined schema, this is great. But if not, you're still making some guesses. And again, let's say we're chunking on paragraphs, that may have the meaning. If you write like I do, I try to make sure each paragraph is a self-contained meaning, but that's not always possible. So then, if you want a method that's fairly balanced, there's hierarchical chunking. And with hierarchical chunking, you can basically define groups or hierarchies in which that you're able to chunk everything over. Now, it's kind of similar to structured chunking, but you don't necessarily know the structure, so you have to give rules to it. And what's nice is that if you're able to define those rules, you're going to get chunks that have like a lot of meaning to it because you've basically defined all the context around a particular point. Let's say each regulation section within the Nevada state insurance regulations. But it also requires you to have domain understanding. And if you have tons of documents coming in and they're all over the place, that chunking strategy may or may not work. So finally, there's semantic chunking, which is going to be the most powerful strategy because it's effectively like using an embedding model. You're able to find the meaning between all the different chunks, analyze the whole document, and then figure out, okay, break it up into these chunks. This is going to give you the best relevancy ultimately when you're performing the semantic searches at the end of the day, but to require more time and resources, it's going to have an additional cost. Likely, as your methods evolve, you're going to end up either with hierarchical chunking or semantic chunking, particularly for mature applications. But all these chunking methods do again have their trade-offs. You want to build a quick POC just to show that something's working. Fixed chunking, cool, that's the way to go. But you're going to have to pick something that's ultimately going to give you more meaning around it. Now, what about structured and semi-structured data? Well, we've already introduced the fact that we can use something like natural language queries to be able to query the data, but maybe there is semantic meaning that you need to unlock by transforming it, and that's fine. It's actually something I've seen our customers do in production environments where they take globs of data within their relational databases or data warehouses, put into like some kind of document. It could be just like, I've seen like literally just like text blobs in databases, but you could use a JSON document or something and transform it into a vector. And then ultimately you can use that as part of a semantic search. And again, that works if it makes sense for your application where you need a different way to be able to unlock that semantic meaning. But keep in mind, it's a pipeline management problem. So that's going to be something that you'll have to continuously manage to keep up to date. So how do you figure out what size chunks to use outside of using semantic chunking where hopefully that's figured out for you? Well, there is going to be a balance. And typically smaller chunks are going to be for applications where the meaning is less important in the sense that simple question and answers. Whereas if you need to get very specific or you have large blocks of code or text or insurance regulations in the state of Nevada, you might need larger chunks to capture that. Again, part of this is that you're going to have to play around with what makes the most sense for your application. But the idea is that you now have some techniques and strategies to look through. And again, if you end up with something like hierarchical chunking, some of that will be answered for you. You may ultimately need to put a cap on the chunk size based upon the embedding model or what costs you want to incur in terms of storing that in the database. Now let's get to vector search. So vector search is one of my favorite topics. I had a breakout earlier today, DAT319, which we do deep dive into this in terms of Postgres. But here we are, about 2/3 into the talk, and this is the first time I'm talking about choosing vector search. And that's kind of the point. Because with retrieval augmented generation, vector search is a component of it, but a lot of the meaning that's coming to your applications are coming from all over the place, from your traditional enterprise, transactional, operational, analytical stores, and maybe from your unstructured data that you've now transformed into vectors. So how do you pick one of these vector search solutions? First, start with familiarity. What you're going to see is at the end of the day, based upon what you're doing, a lot of the performance characteristics are going to be very similar. So go with the selection that you're most familiar working with, because that's going to help with the ease of implementation. Because recall that in terms of the delivering personalization, it's going to come down to the RAG techniques that you're choosing. You're going to start with naive RAG, but ultimately it's going to evolve into advanced RAG, and you want to make sure that you can pick a vector search solution that you feel comfortable integrating with throughout the stack. Scalability and performance may be important, but it depends on the size of your data set. And it's interesting, everyone has a different definition of large in terms of how many vectors you're working with. To me, I feel like it's in the billions range these days, but again, I've been staring at these problems too much for the past 2 years. But I'll hear people say oh, I have a lot of vectors. It's about a few 100,000. But yeah, but all these solutions can handle those very quickly. So this is where familiarity and ease of implementation come back, because really what you could be doing is iterating on delivering those personalized responses in your generative AI applications. But we do offer a bunch of different databases that incorporate vector search. And you can see, like, overall, they offer a lot of very similar features around performance, speed, scale, and different query techniques. And if you need to pick one specifically outside familiarity, it's probably going to be one that solves a particular domain problem. So for example, let's take GraphRag. With GraphRag, if you need to utilize GraphRag and search over an information graph, you're likely going to use Amazon Neptune Analytics because it's built for that exact use case. If you're going to do something involving full text search, that's where you're going to use Amazon OpenSearch Service because it's built for that use case. So ultimately, you want to pick a solution that you're most comfortable with to start. And as you're exploring and architecting deeper use cases, you'll be able to find the right solution for yourself. So finally, index selection. I could spend an hour, 2 hours maybe just on this topic, so I'm going to try to get it down into one slide. So one thing to keep in mind when you're indexing vectors is that you're doing an approximate nearest neighbor search. And approximate nearest neighbor means that you may not necessarily return all the best results. Like you're going to need to measure the search relevancy via recall. So if you need 100% recall, basically you need to make sure that you're always seeing the best candidates that you're searching over. You're not going to use an index. Or you're not going to use a vector index, I should say. You may use a different index. You could use like a B tree in a relational database if you know you have high selectivity, and that's going to give you a very fast search. But if you want to guarantee that you're always getting the best quality results, you're not going to use an approximate nearest neighbor technique. Now, there's all these different vector indexes available. But the one that emerges the most popular is HNSW. Which stands for Hierarchical Navigable Small Worlds. And the long story short with HNSW is that it works for a lot of use cases. First, it's very easy for developers to work with because it behaves a lot like other traditional indexes where you can add and remove data from it and it automatically updates, as long as the index has allowed for the automatic update and delete. Like that's actually a little bit harder to do in HNSW, but it's possible. But in general, from your standpoint, you don't care about that footnote I just gave because it's easy, it just works, it gives high quality results with pretty good performance. Now, you might see that your HNSW indexes grow very large, and it's true, like it is kind of a bulky index. And quantization is a technique that ultimately reduces storage by shrinking the vector sizes down, but it impacts your recall ultimately. So then it becomes like, what are my trade-offs? So I can reduce the storage of my database, and maybe I can get faster responses from my database, but maybe I'm not getting the relevancy I want, and ultimately I need to pay down, the cost of my foundation model because that's where I'm spending the most cost. So quantization may not necessarily make sense for a particular application. So you have to work with your data science team to see, where ultimately they want to be able to spend that time. And finally, other index types may be better if they have high selectivity. So high selectivity is it's an inverse property. If you say something is highly selective, it means you're returning very few results. And if you're returning very few results, you may not want to use a vector index to search over it. There's all these other indexing methods to help. So now we've talked about all these different RAG techniques to personalize the data. We've talked about how to prepare the data. So how do we ultimately get this data flow all together? And I'm happy to turn this over to Siva.
Thank you. Thank you, Jonathan. Still here? So we're going to the final stretch. So where does the context come from? So in a RAG application, as you have probably seen so far, in my mind, it's always about the context. So what you're doing is you're taking the context and supplying it to your application. So let's go back into so where does this come from? It really comes from all your operational databases, your data warehouses, data lakes, and even streaming data stores. Let's take the insurance example, for example, in this case, right? The Horizon Guard example that we've been walking through. Probably there's a lot of information about the customers. The customer profiles are kept in potentially a relational database. All your history, whether it be court history or your policy history or your claims history, is probably in a data warehouse or a data lake. Also, the rules, Jonathan talked about if you're in the state of Nevada, there's a bunch of rules. They're probably in a PDF document in your file store or your data lake, if you will, like S3, for example. Or in some cases, some companies are offering usage-based insurance. In other words, they put a device in your car or install an app in your application, so it transmits all the data based on your driving characteristics when you're driving the car, so they may actually give you a big discount. So that's kind of streaming data that's coming in. All of this data is actually flowing into it. So your DMV, Department of Motor Vehicle, has your licensing information as well as your vehicle records. For example, we talked about a situation where the second car was potentially in an accident. That's because actually the data of the car sales didn't actually show up in the system. There was an issue. So all of this is essentially coming into your sort of the data systems, if you will, in the company. So that presents itself many challenges. These data is in various data silos, and you need to be able to track the lineage. In other words, where did this data come from? And data quality issues, for example, right? If you're getting data from two sources, you need to be able to actually update that and keep that in sync. We need to understand and assess the data quality of the data that's coming in. Also, there's the PII data, for example. There might be credit history that you're getting for a customer. There's social security numbers associated with that. If you're getting your driver's information from the driving department, DMV, there's also the driver's license ID, which is typically confidential, and your name and address details. So all of that, you need to be able to actually, your pipelines need to be able to deal with it, manage it, in some case tokenize this, et cetera, right? Also, there's the identity resolution. For example, the DMV identifies you by the driver's license ID. For example, the credit bureau identifies you with your social security number potentially, and you have a customer ID in your organization that you gave the customer, right? All three things are the same. So you need systems that actually match this together and then come back and say, all of this pertain to the same customer, if you will. So access control, obviously, if you're writing a chatbot application, it needs to access the relevant data with relevant permissions. So you need an architecture that solves all of this. So I've built a lot of big data pipelines for customers. I've codified these 5 rules that has actually withstood the test of time for me at AWS. No new launch or other things have changed it. I'm going to share those with you. So first is, anytime I build a big data application, an architecture feels like a pipeline. There's data going in from one side and answers coming out on the other side. And then what goes in between is the kind of data that you deal with. And typically when you want to build a decoupled system, you build it in a way, there's a processing stage, and then there are 2 processing situations, systems on either side. You decouple this with a storage subsystem. For example, if you're doing a stream processing, you potentially take the data stream, all the information that comes about your driving when you put this device in the car, that's potentially lands in Kinesis or Kafka, right? And then once you land that, then you probably are using Spark, streaming, or Flink to process that. That's the processing stage. Then if you want to do some kind of a graph RAG on top of this, you want to land that data in a graph database, right? So essentially, where you put this data depends upon really, this comes to the second thing, right? In each stage of the pipeline, what you use, the technology or the tool that you use is based on the structure of the data that you deal with. Where do you want to load the data? And what kind of a latency requirements that you want. Like, in other words, you need to understand the access patterns to be able to land the data in the right place. And then the third, but not the least, is you're busy building your entire application. The best practice is if there's a managed service that deal with this entire managing the cluster problem, you should probably use the managed service or even a serverless service. Then you're not dealing with actually spending time managing the cluster, rather than you're building, you're spending time actually enhancing your application. For event or streaming data, it's always the best practice to land a copy of the data in, for example, S3. I call this log-centric design patterns. Even if I've been in the data business for a long time, even databases actually write to the transactional log first and materialize the data in their various systems, right? Whether it be, pages that back your rows, et cetera. So really, using the similar paradigm, keep a copy of the data in S3. Sometimes in applications or bugs, it's always a good idea to go back to the original data and then get back to it. And really creating views, materialized views, is going to be pretty important. Last but not the least, big data should not be equal to big cost, right? Anytime I do a design review for customers, after 20 or 30 minutes, I park the design review and say, let's find out what the cost of this end-to-end solution is. Oftentimes, it's a little bit out of whack. Chances are I'm using the wrong tool for the job, or I have to change the design to fit my customer's needs, right? So when we build data services at AWS, we build them to do their function extremely well at a low cost. Usually when you're using something that is like, big cost, you find out that you're potentially not using the right service, if you will. So with that in place, how is it relevant for, RAG pipeline? Choosing the right data architecture for RAG always entails about actually you creating a serving layer. It feels like a reverse ETL to me, right? You build a serving layer, for example, if you want to materialize the data in the graph database, essentially you'll have to land this in a graph database, though, right? So the real requirement there is, maybe in some RAG systems, you may do tens of requests or hundreds of requests to materialize the semantic meaning of what you're trying to look for. And if that's the case, you potentially need millisecond response rates, right? Like if you do 100 calls, it's 100 milliseconds, it might be okay for the customer to wait. But if you're calling a system that takes seconds to answer that question, you literally don't have the time to answer that question. So your latency requirements for the pipeline dictate where you land this data. For example, typically databases, operational databases take millisecond to get the response back. And then if you're looking for a sort of a data lake architecture, probably landing this in a data lake potentially would be like a second or somewhere around their response rates, right? That's one decision. The second decision is really the backend pipelines. So if I call this data freshness, right? If you're building a backend pipeline, if you want the data to show up in a few milliseconds, potentially you want to stream that data directly to a database or directly write to the database, if you will. And the second option is if you want this to be in a seconds, really actually streaming the data to a data warehouse such as Redshift. We have connectors that stream fire hoses that can actually take data streaming data in Kinesis or Kafka and then materialize that in Redshift, right? I would use that pattern for that. And open table formats are getting popular. And then if you're thinking about landing this data for tabular data access, land this in an open table format such as Iceberg. So if you want the access to be in a minute or so, landing the streaming data into an open table format and accessing that is the right pattern or something that worked very well for customers. And if you have about 5 minutes or more, maybe running a batch job to actually materialize the data in open table format would be the right way to think about that. Now, using these things, I think Jonathan talked a lot about the front-end pattern. I want to summarize this here. So in terms of your application, it's going to keep the conversation history. The conversation history, a lot of customers are using DynamoDB for conversation history, where if you know the details of Dynamo, it has the hash key or the partition key or the range key for doing parent-child relationships. You put the customer ID in the hash key, and you put a timestamp in the range key. It can keep all the conversations for you, and then stick the payload as part of a pointer to an object in S3 or directly in there, or store that compressed. And similarly, your situational context can come from operational databases, SQL, NoSQL, Graph, any database that suits your usage pattern, right? And then your analytics, your context can also come from the analytics system. Typically, it takes a second or so to get that. So it could be through your open table format that, data in an open table format that you access through Athena or Redshift, for example. And similarly, the semantic context is the vector data store, as Jonathan walked through. So what is the backend architecture for updating the context, right? So, this is the sort of the serving layer in the middle, right? And then in the middle, the situational context, if you're deriving through an analytics data store, really keeping the data in S3. I think of this in 3 layers. The very bottom layer is S3, where you keep the files in potentially Parquet file format, and you have store the data in an open table file format. And then there's a data catalog on top of that, and Athena can retrieve this data set very nicely. Also, it allows you to keep all the metadata, the catalog there, the metadata catalog there, Glue data catalog keeps all the metadata that's applicable when you're actually, in some cases, like the text to SQL scenario that Jonathan pointed out, you're aggregating all that data, you're first getting the schema, and then materializing the SQL query. That can really happen if you put that in a technical data catalog. Similarly, if you have streaming data sources, you do your standard stream processing, landing the data in Kinesis or Kafka, and running Spark streaming or Glue streaming or Flink to actually manage the data and put this in an open table format. Or this is also this chunking piece that Jonathan talked about, right? This is the reverse ETL that takes all the data in your data lake and potentially, things like Kinesis or Kafka and lands that in the front-end serving layer. So all that should be pretty familiar to you. And there's nothing different than all that we have done so far in stream processing or batch processing. The only difference is we are really tying this to, surfacing context in terms of a serving layer, for your RAG application. I'll get into a little bit of data governance. As I think about data governance, the idea of data sharing, some people call this, various types of, architectures. It could be called, for example, data sharing architecture, data marketplace, et cetera. So for example, if you think of the example that we talked about in the case of an insurance company, probably the sales department has a data lake. One thing is the chatbot builder can actually build the entire data lake and source all the data and build the data lake themselves. A better pattern would be, potentially, if a sales department has its own data lake, and also the claims department has its own data lake, you could potentially create a data product. Data product typically comprises of, the construct data product, multiple artifacts there. The artifacts could be S3 files, or it could be various tables that you're bringing in there. And then if you could register that with Data Zone, and there is actually a subscription data flow where the chatbot building team can subscribe to these various data products that the various teams are building. What happens is if you use this model of data sharing and governance, when you ask for permission as a chatbot team, when you ask for permission to share a specific data product, the entire workflow, when the creator of the product approves it, all the required permissions, et cetera, that come with it, right? So that is the best practice. Now think of this as, build a data sharing architecture where you can actually think of your entire thing as a data products, and sharing the data products with relevant teams is the best practice there. Like we talked about data quality and lineage, right? For example, one of the business rules for ensuring data quality could be, the claim date should be within the policy begin date and the end date, right? If you're writing a policy in the state of Nevada, that might be some minimal liability coverage required there. All of those are business rules. Your pipeline should be able to actually cater to that. And there could be format things like, the phone format or the policy ID should be unique. You need a system to keep track of that in terms of data quality. For example, if you're using AWS Glue, and if you're doing AWS Glue pipelines, if you will, you can actually, there's a language called the data quality definition language, which is a language that we invented. It comprises of various rules that you can declaratively specify these rules. And then when you run a job, this actually would verify if these rules are met. And you can come up with the data quality score as well. So if you have 10 rules, only 9 rules have been met. When you run this job, then you have a 9 out of 10, which is 90% data quality. The team that's actually building this data product can ensure that the specific artifact that they are exposing meets a specific data quality role. It's pretty important, to understand data quality and then coming up with measures as well. And also, data lineage is going to be important. Like, for example, in this case, there's a data producer, the underwriting team. In an insurance setup, what happens is that I'm going to use that example. So when I give a quote, when the sales department gives a quote, it says, hey, customer, this is the quote ID, here's the premium, right? And then in this case, maybe the underwriting, and it goes to the underwriting team says that, well, within this quote, these are the various policy that I'm going to write for the customer, right? Then there's a policy and a policy ID. So typically they take the premium amount and keep it there in that table, if you will, right? And then when you're creating an embedding, let's say in your application scenario, you're taking a policy that is created by the underwriting department, and it's a PDF document, you're sticking that in your vector store by chunking this one. In that policy document, you might be having a table that has the vector embeddings and also the premium amount. When you find out that the premium amount is wrong, you need to be able to go back and trace that lineage, right? So if you're using Data Zone for keeping all these assets, there is an open lineage, is an open standard for keeping lineage. So any open lineage compatible, technology such as Spark, or even if you're using DBT, can actually keep this lineage. And it's pretty important to understand data lineage as a chatbot building team, for example. With that, I want to pull this all together. Like, this is sort of the end-to-end architecture for RAG as I see it, right? And there's a front end. The key piece here is to come up with a serving layer that can actually materialize the data in the form that can be served to the generative AI application. With that, I would like to pass this on to Jonathan to summarize the talk. I know we went really fast, but I'm trying to fit this within the window and then so you can get out of here on time.
Yep, so I'm the summarization model here. So what did we learn today? We did a lot, right? As we said, this is a L300 talk where you have to get technical and cover a lot of different concepts. So what are the takeaways? I'm a traditionalist. I always like to work backwards from the data But in this case, you need to work backwards from the workflow. How are you bringing the data in? What are the RAG techniques you're using to power the generative AI application? Because your data sources are the data sources here. Like, they're going to ultimately power what that is. And really, the data source selection is going to end up being a data target selection, like where am I moving the data to? And you can iterate towards that, and wherever you can, leverage automation. Also, you can use your existing data. That's the takeaway. You might be hearing like, oh, I got to turn everything into vectors. Guess what? As much as I love vector search, most of the things we talked about today were not vectors. They're the original source data that you have. And you can use that and bring that into your generative AI applications. And finally, automation. As much as you can automate, please automate it. Like, that was probably the biggest mistake I made as an app developer, was I didn't automate enough. It would have saved so much time on operational tasks. So with that, thank you so much. Please give feedback on the talk, and thank you for joining us today.
Thanks a lot, everyone.
Thank you.
Appreciate it.